Today we're going to be learning about frequency distribution curves. This is something slightly new, although it's based on something that you are already familiar with. Think about what kind of graph or plot we could have that shows us frequency, and you should know what I'm talking about. In case you don't, well, here it is, histograms. So frequency distribution curves are related to histograms. They both show frequency. So here we have a histogram showing the heights of black cherry trees. Here are the heights. The y-axis is, of course, frequency. Why? Because it always is. Right? The y-axis is always frequency. But what else can we tell? Well, we can look at this and see that most frequently, black cherry trees are between 75 and 80 feet tall. At least the ones in this sample. How do we know that? Because it's the highest bar. And in fact, we can tell how many in our sample were between 75 and 80 feet. 10. There were 10 black cherry trees between 75 and 80 feet. There were also many trees between 70 and 75 feet. There were 8. We know that in total the trees measured at its lowest 60 and at the highest 90. And we see that the middle is high and the ends are low. So that means that more frequently, black cherry trees tend to grow between 70 and 80 feet tall and rarely grow to heights that are at the far ends of our range, 60 to 65, 85 to 90. It doesn't happen very much, but it does happen. Well, let's look at a different way of telling the same information. Let's look at a frequency polygon. A frequency polygon essentially just takes a dot or a point for the frequency of each interval. So it's the same as a histogram, but instead of using a bar, we're just going to put a point, and then we're going to connect those points. So it looks like that. That blue line with the points, that's a histogram polygon. What information does it tell? Well, exactly the same as a histogram. We can still look at this dot and see that there are 10 black cherry trees between 75 and 80. Still goes high in the middle, low on the sides. So it still gives us the exact same information as a histogram. Usually when we have a frequency polygon, we do it instead of a histogram. So we can take away those bars. So this, again, gives us the exact same information as a histogram. So what's the point of a frequency polygon then? Why wouldn't we just do a histogram? Seems easier to look at. Why do this? Well, the answer is because we might want to compare multiple samples. It's difficult to overlap bars on a graph. You can't see both at the same time. But lines, it's easier. So if we want to compare multiple samples, we might want to use a frequency polygon and plot them on the same set of axes, and we can compare them. So what can we tell now? Well, we can look at Japan is more frequently between 75 and 80, whereas the US is more frequently between 65 and 75. Right? The mode for Japan was between 75 and 80. That was the highest frequency. The mode for the US was between 65 and 75, because both these points were at 8, which is the highest frequency. So from that information, we can say black cherry trees in Japan tend to be taller than those in the US. What about this example here? We have another frequency polygon. We're still comparing heights of black cherry trees in Japan and US. We still have the height on the x-axis, frequency on the y-axis. It is a frequency polygon. So this is interesting though. If you look, almost every interval has higher frequency for US than Japan. The US has more short trees than Japan, but look over here, also has more tall trees than Japan, except for right at this point right here. So if it has more short trees and more tall trees, essentially the sample just has more trees. So the US sample seems to just have more black cherry trees than the Japan sample. So how can we tell? If it's taller, I should say higher everywhere, more frequent everywhere, how can we say which country has the taller trees? Well, we can look at the relative peaks and valleys, right? So the peaks for the US tend to be over here, whereas the peaks for Japan tend to be over here. but then it goes down over here. It's kind of difficult to tell. So that's why we need something else. We need a relative frequency polygon. So this is not a relative frequency polygon here. This is exactly the same thing that we just saw. That's a regular old frequency polygon. Hard to tell. US has more trees in its sample than Japan. In fact, Japan has 62 trees, N is 62 for that sample. And the US N is 130. There are 130 trees in the US sample. We can look here between 79 and 80 or 81. And I should say 81. The Japan had 5 trees between 79 and 81. That's right here. Whereas the US had 7 trees between 79 and 81. Okay, but that doesn't really tell us anything because the US had a lot more trees. So of course we would expect the US to have more trees between 79 and 81. Not because the US has taller trees, but because they have more trees. So just because the US has more trees between 79 and 81 doesn't mean that overall the US has taller trees. That's happening just because the US has more trees in general. So we need to make a relative frequency polygon. In other words, we need to compare these numbers, these frequencies, compare that to how many total we had. In other words, we're going to use percentages or ratios. So the Japan had 5 out of 62 trees between 79 and 80. That's the same as 0.08 or 8% of the total trees were between 79 and 81 feet. Remember, it says 80, but it should say 81. The US had 7 out of 130 trees between 79 and 81 feet tall. That's the same as 5.4%. So while the US had more trees between 79 and 81 feet, 7 versus 5, if you look at the actual percentages, Japan had a relatively higher frequency than the US because 8% of their trees were between 79 to 81 as opposed to 5.4% for the US. So black cherry trees in Japan tend to be taller than those in the US if we look here. How do we get that? Well, Japan had a higher percentage between 79 and 81, so they had a relatively higher frequency between 79 and 81, but we don't care about just that part. We also want to see overall. But look how we changed this frequency polygon. Over here, we don't see the frequency. We see the relative frequency, right? So up here is 16%, 12%, 8%, 4%. So if we look right here, this dot corresponds to 7% of the US trees were very short, as opposed to 3% of the Japan trees. So now we're on an equal playing field. We're looking out of 100. That's what percent means. So it looks like over here, the Japan definitely had higher relative frequencies in the higher ranges. And the US has higher for the lower intervals. So the US had higher frequency for short trees. Japan had higher frequency for tall trees. Although over here things get a little trickier, right? Because the really tall trees tended to be more in the US, although these numbers are very, very close. So it's still not completely perfect, but it's still pretty clear that the Japanese trees tend to be taller than the US trees. Again, we do this by looking at the relative frequencies. What percentage of the trees are tall for Japan, what percent of the trees are short for the US, etc. So this leads us then to, from a relative frequency polygon, it leads us to frequency distribution curves. So these are the same thing. They just look curvy. Why? Because when we have really large populations, things tend to smooth out. they tend to follow predictable frequency distributions that we know, which is what we're going to talk about over the course of this week. So we see this frequency distribution curve shows us that, well, the highest relative frequencies are in the middle for whatever we're talking about here. So if this were black cherry trees and height, then the most frequent heights would be right here, perfectly in the middle, and then very few on the outside. Okay, this is similar to our original frequency curve for Japan, but it's not always going to be higher perfectly in the middle. We might be skewed. If we look at something that's skewed right, also known as a positive skew, we know that that means that there are some possible outliers over here, right? Our mode, our highest frequency, is no longer in the middle, right? Because the middle data is over here. That's where the median is. The mean got pulled really far because of the outliers. Here we have a negative skew, or skewed left, right? We have low outliers. Again, the mode is way over here, not in the middle. The median's in the middle. That's the middle piece of data, right? Because we have lots of data over here, and we have only a little bit of data at each place over here, but this range is higher. So frequency distribution curves can be helpful because if our data is following a predictable pattern, we can make some predictions about our data if we know what kind of distribution curve it tends to be getting close to. If we can, and we can't do that if we have these skews, but we can do that if it looks something similar to this, and that's what we're going to talk about. So a frequency distribution curve shows us the frequency at different intervals, just like a frequency polygon, just like a relative frequency polygon, because it's going to show us the percentages over here. This says frequency, but it's really a relative frequency. So that's what frequency distribution curves are. We're going to be looking very, very closely at frequency distribution curves from here on out. So the important thing to know right now is just that they're showing relative frequency for different intervals for whatever variable we're talking about. So you can think of it as a histogram, you can think of it as a relative frequency polygon. That is the end.